Hello everyone, I'm Rajasri, Assistant Professor, Department of EEE, working at MLR Institute of Technology, Hyderabad. Today, I'll be teaching GTO, its symbol, structure, IV characteristics of GTO. This is the symbol of GTO and we can represent GTO in these two ways, either like this or like this. These are both the symbols of GTO. And GTO, as I told you, it is a gate turn-off thyristor. Why it is the name gate turn-off thyristor? See, GTO is similar to that of SCR, where SCR it is only semi-controlled switch, whereas GTO it is fully controlled switch. That is, in order to turn on the SCR, we provide a gate pulse, whereas in order to turn off the SCR, we require force commutation circuits, whereas GTO can be turned on using a gate triggering pulse and it can also be turned off using the gate triggering pulse. So we can control the switch using the gate triggering pulse. That is the reason this is termed as fully controlled device. And this is a fully controlled switch which can be turned on as well as off by a gate signal, and GTO it is a PNPN device, can be turned on similar to that of a SCR by a positive gate pulse. If you take in SCR in inverters and chopper circuits, in that case, as I told you, we may require a separate force commutation circuit which adds to the cost of the existing appliance. Whereas if you make use of GTO for the same application, in that case we can simply apply a negative gate pulse of certain magnitude in the sense about 20 to 30% of forward anode voltage. In that case we can simply turn off the GTO, or otherwise we can apply about 20 to 30% of anode current, negative anode current, in order to turn off the SCR. So there is no need of commutation circuit, force commutation circuit in inverter in order to turn off these GTOs. And if you see, these GTOs are compact and it is costless and simply a negative current required in order to turn off a GTO, and whose amplitude will be a bit large, that is 20 to 30% of the anode current is required in order to turn off the GTO. And example, let us consider a GTO of rating 1000 amperes. In that case, we need a negative pulse of about 250 amperes peak in order to turn it off. And coming to the structure of a GTO, which is just similar to that of a normal SCR. If you see, this is the normal SCR, which is PN device, and it has got three terminals, that is anode, cathode and gate terminal. And if you consider the structure of a GTO, let me draw the structure of a GTO. This is PN device, where anode will be connected to this particular P plus layer. I mean, the doping level of GTO will be more when compared to that of conventional SCR, and N layer is similar, and the N layer that is lightly doped, and again over which we have P layer, and here in GTO we will connect the cathode to the N plus layer. To the N plus layer, we usually connect this particular cathode terminal. And then to the P plus layer, the doping level of the P layer will be increased, and then a gate will be connected to this particular P plus layer. In that case, this is the structure of a GTO now. And usually the turn on will be with a positive gate pulse, and turn off will be with a negative gate pulse, and this GTO is usually 10 times faster when compared to that of a normal SCR. And if you see, GTO is not as reliable as that of SCR. And here, whenever gate voltage is applied, that is when anode is made positive with respect to cathode. In that case, the GTO will be in the forward bias mode, during which this layer will be forward biased and this is reverse biased, and again this layer will be forward biased. And when GTO, we need to bring the GTO into the reverse bias mode. Under reverse bias mode, we need to make anode negative with respect to cathode. In that case, this junction will be reverse bias, this will be forward bias, and as well as this junction will be reverse biased, similar to that of a conventional SCR. And in order to bring this particular GTO into the conduction state, in that case, we need to make anode positive with respect to cathode, and then gate voltage need to be applied. In that case, we will have both two forward bias junctions and one reverse bias junction. By applying the gate current of required magnitude, we need to break that particular depletion layer and then bring the device into the conduction state. Now, let us see the characteristics, IV characteristics of a GTO. And let us see here we are applying the reverse bias mode, that is by making anode negative with respect to cathode. In that case, what happens, both the junctions will be reverse bias and middle junction will be forward bias, during which certain amount of leakage current will be flowing through the device. And the moment when it reaches reverse blocking voltage, in that case the high amount of abrupt current will be flowing through the device, and this is that particular reverse bias current which is flowing through the device. And the moment when we need to bring the SCR into the forward bias state, we need to bring the GTO into the forward bias state. In that case, what we need to do, we need to make anode positive with respect to cathode. In that case, both the junctions will be forward bias and one of the junction will be reverse bias. And during this particular state, leakage current will be flowing through the device. And the moment when it reaches forward breakover voltage, at that instant, when the required magnitude of gate current is applied, in that case, the device starts coming into the conduction state, and thereby the GTO starts conducting the forward current. And now, the moment when I intend that, see, previously it was in a reverse forward blocking mode, and at this instant, if we intend to turn on the SCR, in that case, we will be applying the required magnitude of gate current and thereby bringing the GTO into the conduction state. And the moment when we intend to turn off the SCR or GTO, in that case, what we do is we apply the gate current of negative pulse of about 20 to 30% of the forward anode current. In that case, we can bring this particular SCR into the off state. We can bring this particular GTO into the off state, and the current will be now below to that of the latching current or holding current of the device. And if you see, latching current of GTO is only 2 amperes, which is very, very high when compared to that of normal SCR. If you take normal SCR, whose current will be about 100 to 500 milliamperes. That is, latching current will be about 100 to 500 milliamperes if you consider for the normal SCR. Whereas for GTO, the same latching current will be in the range of 2 amperes, which is very high when compared to that of the normal SCR. So that is the only difference between SCR and GTO, where GTO is a higher rating SCR. Coming to the characteristics, see, here on-state voltage drop of SCR will be about 1.5 volts, whereas for GTO it will be about 3.4 volts. And the turn-on time of SCR will be about 8 microseconds, whereas for GTO it will be very less. It will be only 2 microseconds. And the turn-on time, that is gate current for SCR required, it is only 200 milliamperes. And for GTO, the requirement of gate current will be about 2 amperes. And the turn-off time of SCR is 150 microseconds, whereas here for GTO, it is 15 microseconds. And operating maximum frequency of SCR will be 100 Hz, and for GTO, it will be 1 kilohertz. The frequency, high frequency applications, we can make use of a GTO. And coming to the application part, as I told you, in inverters and chopper circuits, we can comfortably make use of a GTO. And here we don't need any external commutation circuits, or we can also call it as forced commutation circuits, are not required if at all if we are making use of a GTO. In the next lectures, we will be seeing rectifiers. Thank you.